Oh,
So, okay, so let me talk about that. So if you're looking at this sheet, I have semester courses and year-long courses divided. Bio, if you look at the very, very bottom little point that I have on the entire sheet, so bio and earth science can be taken as a year-long course. And almost every single person does, right? Like, it's actually rare that anyone takes bio or earth science as a semester course, but you technically can. Each semester is different, and in general, people take the full year, but it's not mandatory. So for whatever reason, if there's an obscure reason why you'd only want to take a semester of bio or a semester of earth science, that's allowed. But no, if you're taking bio, take the whole year, right? That's generally what people do, and that makes the most sense. Especially if you're college bound. If you guys are college bound and you have not had bio, I don't think there's anything to think about. Take bio. That's my 2 cents. What'd you say? I don't like it, but chemistry is, you've reached the end of your chemistry career at Wausau West, whether you like it or not. Sorry guys, I don't teach another class. It'd be organic. It'd be so much fun. Oh, I'd love to teach organic. It'd be great. But it's not a choice, so sorry. Make it a choice? Yeah, I think trying to justify to the school board that we need a 3rd year of chemistry would be really tough. Because there'd be like 8 people in it every year. And then they pay me full salary to teach 8 kids.
AP Chem, if you take AP Chem, you have to take.
Okay, then literally the only people that could get into that class would be, you'd have to take chemistry as a sophomore.
That's true.
You'd have to take AP Chem as a junior, and then you would take that class as a senior.
Yeah.
This feels not logical. Plus, it's literally a second year college course, so there's that too.
Yeah, we should talk to the board.
No chance.
Jeez, in 1 year.
Yeah. Anyway, so if you filled this out and you feel confident, we'll just turn them in later at the end of the hour. I'll try. If I don't remember, please somebody remind me. But think about what you want to take. If you want any recommendations or if you want to talk about a class, I know a little bit, not a lot of it, but other people have taken them too. Talk to your peers, obviously. That'll help quite a bit, I imagine, too. Anyway, so let me make sure I'm recording. I'm recording. All right. So let's get into 5.2. We started this unit, and this is kinetics again, right? Chemical kinetics. The whole darn thing is about rates of chemical reactions. We're just going to expand upon that a little bit. Today's topic's not really anything too new or different. The last 2 problems on this thing are basically giant practice problems of what we kind of finished with yesterday. So we'll get there eventually, and I'll give you guys a shot at trying to solve these things. But let's look at a couple different things, and then we'll kind of get back into the stuff we were just doing, and 5.2 is not too extravagant. So anyway, let's go. So the rate of a chemical reaction can be affected by a couple different things, all right? And these are pretty intuitive, actually, I think. It makes sense, for example, that if I change the temperature, a reaction might go slower or faster. That feels pretty logical, right? If I have a chemical reaction going on and I'm cooling it down, intuitively, what would you think would happen to the rate if I'm lowering the temperature of a chemical reaction? Yeah, you're right. Okay, it's logical stuff. If the temperature is lowered of a chemical reaction, it's generally going to proceed more slowly. If I increase the temperature of a chemical reaction, it's going to proceed more rapidly. Okay, pretty logical stuff. A couple other things, if you change the concentration. Okay, we're looking at the rate law, that equation, right? Rate equals K times the concentration of the reactant times to the power of N, which is the order. If you mess with the concentration of the reactant, the rate will change. Okay, the rate depends upon what that molarity is. So if you change it, it might go faster, it might go slower. It just depends upon the order and the relationship of those 2 things. A couple other things, surface area, we'll talk about that in just a little bit. Catalysts, you've heard that word, right? What is the catalyst? You probably know it. Maybe. Just a generic. What's a catalyst? Oh, come on. What does a catalyst do? Huh? What's a catalyst do? It starts everything? That's very, very close. Very close. Anyone else? You're super close. It speeds up a chemical reaction. Okay? A catalyst is something you add that will increase the rate of that reaction. We'll talk about that. The last thing is volumes and pressures. These can be changed and will mess with the rate of gaseous reactions, right? So if I have a couple gaseous reactants, couple gaseous products, everything's in the gas phase. If I'm increasing or decreasing volume, which in turn increases or decreases pressure, it affects how fast things are going to occur. And that kind of makes sense too. So long story short, there's factors that mess with the rate of how fast reactions go. Generally speaking, these are intuitive. So what you think is going to happen is probably correct. Like when I said temp goes up, right? Or temp goes down. It's logical. Yes, it's hotter, so it's probably going faster. Yeah, you're right. All right, so let's look at, what am I doing with this? Let's try that. Anyway, so when the concentration of the reactants changes, the rate's going to change, and that relationship, the order, is going to tell us how much it's going to change. When the tempo of a chemical reaction is increased, the rate of the reaction will increase. When the temperature of the reaction is decreased, the rate of the reaction will decrease. Now, we know that. I just asked you that. Why? Okay? Why? Think about that. If I have increased the temperature of the reaction, why does it go faster? If I have decreased the reaction or the temperature of the reaction, why does it go slower? Think for a second. And then talk to your neighbor. And if you don't have a neighbor, yell at your neighbor. I don't know. Sorry, people at home. I know this isn't possible for you.
See, I don't like. Yeah, they're not real close.
All right, what you got? Somebody offer something up here. What do you think?
The particles are moving quicker.
Okay. Okay, so particles move faster at high temperatures, right? So this is at high temp. Oh, missed an I. Plus, did I spell that right? Did I? I hate that CLE, CEL, CAL nonsense. I don't teach English, so I apologize if I spell something wrong. Okay? Particles are moving faster. Now, what does that mean? Or what does that do? Why would that make the reaction go faster? More kinetic energy. Now, well, let me ask you this. Let me ask you something else. If a chemical reaction is going to occur, what has to happen? That's true. I've got one reactant, I've got another reactant, and they're going to react. What needs to happen? They got to smack one another, don't they? They kind of need to be either like in the general location or close to each other. So if things are moving faster, what's going to happen is that's going to lead to more collisions. Okay? More reactant molecules are going to bonk into other reactant molecules, which means more reactions are going to happen at a faster rate. So I'll say it like this. Higher temp, particles are moving faster, completely agree. And as a result, okay, you get more collisions between those particles. Okay? Cold temp is the exact opposite, right? You slow them down. So now they're colliding less frequently, meaning less chemical reactions. We'll talk a lot more about collisions and what needs to happen in order for a chemical reaction to go. We'll talk more about that. Might be 5.3. I forget where that shows up, but it's coming. Okay, that's a part of this unit. So anyway, this is intuitive stuff, though, right? That feels like it makes very logical sense. I hope. Oops. Damn. All right, here's another hypothetical. I'm attempting to react aluminum and hydrochloric acid. I have aluminum in two different forms. I have aluminum in a powdered form, like ground up a fine powder, aluminum powder. And I have aluminum like aluminum foil, and I just crinkle it up into a ball. Okay? So I have a ball of crumpled aluminum foil, and I have aluminum powder. I mix both of those sources of aluminum with hydrochloric acid. Which of these do you think would react more rapidly? Think about it. And then talk to each other.
Because there's so much. What do you guys think?
Sorry.
I don't agree with you, but I don't know if it's.
Oh, it's definitely because of surface area. You said surface area?
Yeah.
Yeah, aluminum.
Because it's small.
Because it's like,
It's grand.
yeah, a crumpled. Yeah, because the crumpled aluminum, like the inside aluminum can't react with the.
He's saying it's easier to get to all of them.
Yeah, like he's gonna explain it in a second.
You're absolutely right. So I overheard Luca, he was the loudest. So which of these would react more rapidly? The powder one, it would. Now, again, why? Okay, why, right? We got to answer that part of this too. And it has to do with surface area. Let me go a little bit further, because that's kind of a generic, broad statement that doesn't really answer it very well, right? If I have aluminum in a powdered state, I have way more aluminum atoms exposed to the HCl, right? In order for a reaction to go, I need the aluminum and the HCl to collide or be near each other, come in contact with one another. In an aluminum ball, if I just crumple up aluminum foil, the exterior aluminum atoms are exposed to the HCl, but the interior of that crumpled ball, the HCl is not going to be really able to get at. So I have way less aluminum atoms in contact with hydrochloric acid. In a powdered form, I have extremely greater amount of aluminum atoms exposed to the HCl. So more reactions can happen. It's just a quantity thing, right? So it's definitely this, and it has everything to do with surface area. Okay, hopefully my verbal explanation is way better than the word surface area. And I hope that makes sense. Questions at all on that? Seems logical, right? Again, everything in this talk today is a logical outcome. Anything from you guys? Okay, sweet. What did I say a catalyst was?
Spreads the chemical, or speeds of the
Okay, catalyst is a substance that increases the rate of a chemical reaction. Now, it needs one more extra chunk to the definition. Okay? Yes? So, a catalyst speeds up a reaction, and it is also not used up. In other words, the catalyst doesn't change when the reaction's all done. It's not part of the chemical reaction, so to speak. It's just there to make it go faster. Does that make sense? So the catalyst is not used during the reaction, or used up, maybe I should say. Hold on. Put the word up in there. Okay. That's an important piece of this too. Catalysts don't actually take part in the chemistry. It's just a separate chemical that's also there that allows it to go faster. We'll talk about how that happens because that's kind of curious, right? It sounds kind of weird, like, well, if there's another chemical there, why isn't it actually doing, how does it make it go faster if it's just also there? That feels weird. So we'll talk about how that happens later. That's towards the tail end of the unit. I think that's 5.9 or 5.10, but we'll talk about that too. All right. So let's look at a couple more examples here. This is more similar to yesterday. It's related to rates of reactions again. We're going to do a couple of average rates of chemical reactions. And again, this is where we're like finding the slope of concentration versus time. But the problem with the slope of that is generally these are not linear graphs. Okay, so we'll deal with that later, but it's an appropriate or a good use of thinking, I guess, to go through this motion. So hydrogen peroxide will decompose into water and oxygen gas. All right, if you've ever seen the demo of what's called elephant toothpaste, have you seen that at all?
Yeah.
Right, they like mix two things together and it goes and it shoots a bunch of foam out. Okay, that's using hydrogen peroxide because when it's all done reacting, what you get is water, and the oxygen is what increases the volume of the foam or the bubbles really, really rapidly. So, side note, if you care. We're going to calculate the average rate of decomposition of hydrogen peroxide between 0 and 21,600 seconds. Kind of arbitrary. But here's a little data table, and I want us to get the rate over this first interval. Now, rate is measured in what for chemical kinetics? What is the rate? What are the units or label of rate? Change in what over what? Y over x. Yep, what's my y, what's my x? And if you look back at yesterday's page, there's no way to have, you probably can't find it. I think it's in there like 14. The change in concentration over the change in time. Yeah. So here's concentration. Here's time. Let's take the change in my concentration. Okay, and I'll even go like this first, because really, if this were on a graph, right? If we had graphed the concentration versus time, it would be slope. It would be y over x, just like you've always done. Concentration is here. This is decomposition, right? This is a reactant. So we should totally expect that the rate is negative. But if you remember, chemists don't like that. So they switch the sign. Okay? So we are going to flip the sign of this average rate because this is for a reactant and it will give us a negative rate, which chemists are just, they don't like. So we have a final concentration and initial concentration, a final time and initial time. You don't need me, that's pretty easy math. Knock yourself out. What's the average rate over the first 21,600 seconds?
Yeah.
What you got? You're being great. You're good.
2.31.
Sounds about right. Any second on that?
Yes.
Cool. 10 to the negative 5. Sorry, it's kind of smushed over there to the right. The label is moles per liter times seconds. Now, do you have to write it that way? No, you can write it big M over S, because molarity is capital M, right? That works too. Doesn't matter to me. You can write it capital M multiplied by S to the negative 1 power. It's all the same stuff, right? I mean, you can label it a couple different ways, depending upon whether you keep molarity as like one unit or you split it up. And you can use exponents for denominators, and it's up to you. Okay, it doesn't matter. But assuming that it's correct, obviously, then it matters. But anyway, that's the rate over the first 21,600 seconds. Now, when we do it this way, this is an average rate. So on average, over that time interval, it's going this fast. Sorry, freaked out. Okay, on average over that time interval, it's going this fast. Is it always going that rate? No, I bet you early on it's going faster than that, and towards the tail end of these 21,000 seconds, it's going slower than that. It's not a linear graph. It really never is. So this is an okay way of doing things, and we get an average rate of a chemical reaction. But a better way of doing this is using the rate law, like we kind of started doing yesterday. Okay, we'll get to that in a slide or two. Use the rate from part A to calculate the average rate of the production of oxygen over that same time period. This is the hydrogen peroxide. In this reaction, we also produce oxygen gas. I didn't give you numbers for oxygen. I could have, but I don't need to. If the hydrogen peroxide is getting used up at this rate, what would you expect the oxygen rate of production to be? Okay, if the hydrogen peroxide is getting used up at a rate of 2.31 times 10 to the negative 5th moles molarity per second, how fast do you think we would be producing the oxygen gas in that chemical reaction? Yeah, I think we said this earlier this year. The bulb's definitely going out on this one. Thankfully, I just hope it doesn't go out during my class.
No, because it's H2O.
Okay, so I hear conversation. Good.
Weird.
Now the question is we have a ratio, right? I have 2 H2O2 and 1 oxygen. I have a mole ratio of 2 hydrogen peroxides to 1 oxygen gases in my balanced chemical reaction. You're absolutely right. We're going to use those coefficients. But now the question is do we make oxygen twice as fast or half as fast? Is this getting produced twice as fast as that is going away? Or is this getting produced half the speed as that is going away? You're correct. Half. It should be going at half the rate. Now, if you want me to prove that a different way, we can totally set this up factor label style. We have moles right there. We have moles in our label, right? We can just switch from moles of H2O2, which is kind of hidden. I didn't write H2O2, but it is. This is moles of hydrogen peroxide. I can convert these moles into moles of oxygen, right? And in theory, that ratio should totally work out. So if I did that, I didn't leave myself much space. But if I did that, I would have 2.31 times 10 to the negative 5 moles per liter times second, blah, blah, blah. Okay? And then I can convert this from moles, hold on, moles of H2O2 to moles of O2. Okay? What's the ratio? 1 to 2. It's half, right? We verbally talked about that, but the math shows the same thing. So if I divide this by 2, my rate of oxygen production should be 1.15. Do we round up or down? I don't know what the other digits were here. 6? Oh, that makes sense, I suppose.
What's it? 4.
Ah,
0.00.
It's 2314.
okay. So is that a 5 or a 6? Divided by 2. Gotta be a 5. Thank you. That was.
Check my math.
Okay. So the top one there, is it right or not? April, what I do?
Oh, that's right. That's good. It adds up. They're good.
Good.
See,
So-
Sorry, just keep going. You don't need to- It's fine.
Okay. So we have the rate of hydrogen peroxide and we have the rate of oxygen. They can be related. They are absolutely relatable based off of the coefficients, just like a lot of things we do, right? We can compare moles. We can eventually get from grams to grams. You can get from atoms and molecules and all that good stuff and back to label. The rate, it also works. If I know how fast something is being used up, I can also calculate from that rate how fast something is being produced. Now, one thing I will caution you on is this is a reactant, this is a product. In reality, those have opposite magnitudes. You know what I'm saying? We flipped the sign on this one. Okay? But it is opposite. This is a rate of like consumption or a rate of like getting used up. This is a rate of being produced. They're going in opposite directions. So be a little cautious with that. But this one should be used up twice as fast as that one should be produced. And that's just based off of our ratio of coefficients. Make sense? Cool. Do the next one. Part C. Do the same exact calculation, but instead of the first 21,600 seconds, do that average rate calculation for the next 21,600 seconds, 500 seconds. 600? 600, sorry. Yeah, you can't get that. And then, well, you can always, tell me you want to switch it to.
Okay.
I won't give these to your teacher, your home teachers until probably at least a week.
All right.
Yeah, I want these in their hands before, these are the 4. I already see physics, you can do whatever you want. Did you go there? You can, by the way, no one signed up for 2 science classes.
Which one should
I mean, I think I'd recommend bio, only because bio is generally more applicable to college. So that depends, right? If you're like engineering, you think so? If you're going to go into engineering, I'd like to sounds like.
I don't really like class.
Yeah, you need them all. And, crap wood eyes.
That's it.
Okay, what's the rate of the hydrogen peroxide getting used up for the next chunk?
1.5 or 1.5.
Okay? Right? Now, the same ratio applies here, right? We're looking at a different interval, but that ratio is still 2 to 1. So, with that said, for the second chunk, we could set this all up, or sorry, we could do the ratio thingy up here, but really it's just cut in half, right?
Yeah.
That's all it is. So when you cut this in half, the rate of O2 should equal what? We've got to switch our scientific notation, right? Okay, and this is dropped. Now, careful, right? Scientific notation can be confusing. That is half of that. It is. You might have to do a double take or, slow down a little bit to realize it, but this is half of that. Okay? It looks weird because that's a 5 in the front and that's a 1 in the front, but again, that shifts the whole decimal by a factor of 10, right? So it just careful, caution with your scientific notation every now and then. It can throw you for a loop. So this, let me recap this slide before we move on. This is average rate. It's your slope, change in concentration over change in time. It's the average rate over an interval. You can find the average rate and then use the ratio of coefficients to solve for the rate of something else. That's all we did in the second half of both of these questions. Okay? So given the following fake reaction, if the initial rate of decrease in X is such, and see how I told you can label it dumb ways? Sure, you can label it that way. It means the same thing, right? It means the same thing. What is the rate of initial production in Y? X decreases at this rate. How fast does Y get produced? Go for it. The ratio of coefficients is everything. He's down here.
Just so you know, it's a 6. But everyone else thought me out.
It is a 6. At 1 point, it should be 1.6. Yes.
That look good? It's definitely a 6. Here, I'll make it worse by keep overlapping it. Thank you. It's my 6th year teaching. I get better with each year. Should have seen it the first year. It's actually kind of funny. I talk to my first year kids every now and then. Like a couple of them still reach out and they still have fond memories of me. I'm like, well, that's good because can't imagine I was very good at my job. Sometimes just being a decent human is half the battle, I think. I think I do okay at that most of the time. Okay. This is in terms of X. I want to convert my moles of X into my moles of Y. It's literally a factor label mole ratio situation. So that's the rate I want, or that's the rate I start with. That's moles of X. On the bottom, I want to get rid of the moles of X and convert it to the moles of Y. What's the ratio of Y and X? 3 to 2. So I would imagine that I'm producing Y at a faster rate than I am using up X. And that makes sense, right? I get 3 of those for every 2 of those that I use. So what do you get? Punch it in. What's the answer? Okay. What's the moral of the story of the last two problems that we did last slide and this slide? You can compare rates using coefficients. If you have the rate of a reactant or a product, you can compare it to the rate of a different reactant or a different product, just by simply setting up the ratio of the coefficients. All right. 3 and 4, let's have some fun. Two pretty good sized problems that are effectively doing what we did yesterday, except for they're real. Look at real chemicals, no longer placeholder A's and B's and Y's and whatevers. What I'd like you to do is figure out the order, as A is asking you to do. Write out the rate law, as I think B is asking you to do. Let me scroll down. Hey, look, find the rate law. Good deal. And then C, what's the value of the rate constant? And then D, I'm going to mess with it. How does that change the rate? Try. I'll pick you up in a little bit here, but see what you can do. If you need to flip back to yesterday's note sheet, please do so. Okay, you're starting with the method of initial rates to get the orders. In turn, that'll get you the rate law. Once you have the rate law, you want to plug numbers back in, solve for K. And then that's kind of the whole thing. So see what you can do. Go for it. Talk to each other if you're in the room.
Ow!
That was an accident. I didn't mean to do that. That was. I asked her a question.
Like that. See? So this one's from-
That's what I was compared to.
I got it.
Awesome.
And then you multiply it by 3 squared. And then you get that.
It's a little trickier with weird numbers, isn't it?
And then we go.
No.
Yes, because then it's why are we multiplying? It's like a constant. You have to and try and that's what I said. That's for the right, so that's to the second. Oh, you're doing.
Wait, you were doing the you were going from here to here?
Hold on.
Okay, so that's why.
And that's what I had. Persistent work. Oh my goodness.
So that's three.
Yeah. And then you have to do trial 1, trial 2 for all two. So that's what I thought. See, I thought you were going to order. What do you mean going to order? I'm going to order a table. A table? Yeah, this is the first one, a table. The first one. Oh.
Oh my gosh.
See, and then I three, so I'll just first order. Okay, because 3 times 3 is 9, so then you go to the next two that correspond to it. 3, and now you're. Thank you.
Okay, have we figured out the 2 to the 8 or the 8 to the 2?
That's what we just did.
What is it?
It's 3.
3.
I'll just multiply. Well, okay, but look. Look, the order. This one's second. Hey, bro, don't worry about the exponents on those. Not at all. Not worry about
Yeah,
that.
don't do
Only look at those.
that.
You do, like, you know.
Okay, so then.
Right, no, and then K. Oh, I did that. I did that at the first one. I'll just draw an arrow. No, there's only 2 reactions. Look, when you do this, it corresponds to this. So then that's where
Maybe I wanted to go that way.
Yes.
To get from here to here, okay, I know my molarity changed by a factor of 3, right? I held nitrogen monoxide constant. This changed, that tripled, so I know that when this triples, the rate should change by the exact same factor, right? Raised to a power. So I write this in automatically without even thinking. Now the question is what's the power? I don't know about you, you're probably not the best at doing scientific notation in your head. I would assume not. But if you can just punch it in, right? Take that number, multiply by 3. Does it equal that? Good. That means it's first order. If it didn't, we'd have to go further, right? Then I would take that number, multiply by 9, and see if it equaled that. And then take it, multiply by 27, and see if it equaled that. So on and so forth. But this, 8.52 times 10 to the negative 2, multiplied by 3 to the first power, does give us that. This is first order in terms of oxygen. Am I making sense?
Yeah.
Am I?
Oh, yeah.
This one, trial 1 and 3, those are constant. Nitrogen monoxide is changing and triple. Again, without even thinking, I'm going to instantly just write this in because I know it has to be the same factor raised to a power. Again, looking at it, I have a hunch it's not the easiest to see, but just guess and check it in your calculator. Take that, multiply by 3. Well, we got that, right? We already knew it. So take that, multiply by 9.
Yeah.
Yeah, that's what we get. That's 3 squared. This is second order. Cool? So now we know our orders. So as a result of that, okay, by the way, give details of your reasoning, explaining blah, 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 blah. That's just the arrows. That's all I need. I don't know, right? Some indication that your brain is thinking. Okay, what's the rate law? Rate equals K multiplied by NO squared, because it was second order, multiplied by O2 to the first. This is the same thing we did yesterday, right? It's just that we had funkier numbers and actual real chemicals. All right. Now, determine the value of the rate constant, K, for the experiment. What do? How do I solve for K? This is the very last thing we did yesterday. Not very last thing, I should say, because we did the whole unit thing, but how do I solve for K? What do I have to do now?
Take a trial and put the numbers.
Yeah, take a trial and put the numbers in. Does it matter which trial? Now, in theory, that answer is no, it doesn't matter, because again, they should all be the same in terms of like how they work out mathematically. If we did this in a real lab, it's going to drift just a little bit. It would, because, you know, real data doesn't always like, you're not going to get 100% perfect data each try. But I don't know, whenever you're asked to solve for K, I just pick trial 1 because that feels like the thing to do. I don't know, right? It's the first one, so I'm just going to use that. So I have a molarity of NO equal to 0.02. So, oh, I'm sorry, my rate. Rate is 8.52 times 10 to the negative 2. Oops, that's not a 2. This equals K, I don't know that, multiplied by NO squared. NO is 0.02. Interesting things that I have. Sure. Multiplied by the molarity of oxygen. What's that? I don't want to scroll up again. Okay. Do a little bit of algebra. And K equals. Actually, hold on. Let me switch this over. What do you get for K? You enter it? Oh, okay. When you get it, let me know. $7,100. So can I do 7.10 times 10 to the third? What's the label of K? It sure is something. It sure is something. What's the overall order? 3. Then the label of K should be liters to the 1 to the order minus 1, so liter squared, divided by moles to the order minus 1 squared times seconds. Okay, that's wow.
Is the liter, so the moles are multiplied by S?
Correct, in the denominator.
Okay.
Seconds, yep, yep. We okay over there?
Yeah, I'm sorry, I'm just looking.
Well, you're looking like you're trying to, you know, find something that, like I said, was wrong.
No, I'm just looking. No, I'm just looking back because I write notes as you talk to understand why.
Okay, we're good.
Because it like.
What do I got for time, by the way?
You got 2 minutes, 3 minutes.
Okay. Now, if you don't like that, right? If you don't like that, just doing it like off the top of your head. I don't really recommend it that way, honestly, when you're learning it. It's kind of tough to just pull that out of the thin air. You can, it's freaking out again. You can do the whole thing where you just set up this equation with literally nothing but units, right? That's how I taught you yesterday. I know rate is moles per liter times second. I don't know what K is. I know that this is molarity squared. And this is another molarity. So I'm going to say this is molarity Q, right, on the product side. What needs to go there to match this, right? What does this label have to be to cancel this stuff out so that I end up with this? This must be, right? So again, if you get stuck on the label of K and you don't want to just pull it out of thin air, memorizing like order -1 nonsense, you can set it all up. Set up the equation with no numbers and just labels and fill in the blank for K. And I hope that makes sense. All right, let's sanitize. Have a lovely day, people online. Thanks for joining me. I appreciate it. Have a great weekend. Nothing tomorrow except for conflict res. So if you got conflicts, come talk to me tomorrow.
Have a good weekend, Mr. Brosnan.
Thank you. I appreciate it. You too.
Oh my gosh, so bad. I know we're playing, so that's why I'm so quick. Thanks.